A very warm good morning to one and all. I am Atira, Department of Applied Science and Humanities, Universal Engineering College, Valivattam invites you to the last day of our 5-day faculty development program on discrete mathematics, graph theory, and its applications. Thank you all for joining us for today's session. Today's topic is dominations and its variations in graph. And the topic will be presented by Dr. Seema Varghese, Associate Professor, Department of Mathematics, Government Engineering College, Thrissur. And a little few words about our guest. Dr. Seema Varghese is presently working as Associate Professor in Mathematics Department of Department in Government Engineering College, Thrissur. She has 17 years of experience in the teaching field. She has worked in Government College, Chalakudi, Kusat, Government Polytechnic College, Kodamangalam, and College of Engineering, Kidanganur. She did her PhD from Kusat in 2011. She has 3 national and 1 international conference paper. She has published 2 international journals, and her publications are: the first one is Power Domination in Honeycomb Networks, and the second one is on the planarity of iterated star line graphs, AKCE. Her areas of interest are in graph theory. Before we getting started, let me remind you, if you have any doubts during the presentation, please type them into the question box in your Zoom control panel, or you have the option of raise hand in control panel for asking your doubts. And also, I remind you that we will have time for questions at the end. Now, I welcome Danya ma'am to share a few words. Danya ma'am, please unmute. Okay.
Okay, Adira.
Yes, ma'am.
Good morning to all. I am Dhanya, coordinator of this FTP. This is the last day of our five-day faculty development program. As the coordinators, we have tried our maximum to make this FTP a really incredible one. We have presented the best faculty in front of you all in all the previous days. Today also, we have another eminent personality, Dr. Seema Varghese from Government Engineering College, Thrissur. Her presentation topic is Dominations and its variations in graph. I hope today's session is much more interesting, especially for research fellows. With immense respect, I warmly welcome Seema ma'am for today's lecturing. Welcome, ma'am.
Thank you, Danya. Am I audible?
Yes, ma'am.
Okay. So, sorry for being late. I had some technical problems here. It's okay. And first of all, let me congratulate the management and staff of Universal College for doing such a wonderful effort, bringing together all the research scholars, faculty, and students in one platform. And I would also like to thank them for giving me an opportunity to present my areas of interest. So let us start. I'll just share the screen. Excuse me, can you see my screen?
No, ma'am.
Now is it okay?
No, ma'am. We can't see.
Okay.
Please. Okay. Ma'am, can you please click on the share screen?
Yes, I have done it.
Okay.
I have shared the entire screen, but I couldn't.
Ma'am, please click that allow button. Allow. Yeah.
Now, can you see my screen?
Yes, the emblem of Universal Engineering College. Yeah, now domination and its variations in
Okay.
graph. Okay.
Okay. Yes.
Okay,
So,
ma'am, can, yeah, Control A, please. Control L to make it full screen. Yeah.
okay.
Okay, ma'am. Okay,
Yes.
thank you.
Okay. So let us start. Today I'll be talking on domination and its variations in graph. It all started with 5 queens. And let us have a peep into the history of the domination. Ideas of dominating sets originated from the game of chess in India over 400 years ago. Sets of chess pieces which cover or dominate various opposing pieces or various squares of the chessboard attracted interest of chess lovers. Later, this problem was focused on queens. In 1850s, chess enthusiasts of Europe, they came up with a problem. Actually, they had two parts of that problem. The first question was like this. It was a puzzle. It was like this. Determine the minimum number of queens needed on the chessboard such that every square is either occupied by a queen or attacked by a queen, or it is dominated by a queen. You can use the word dominated in the first session itself. Okay, now the thing is that these chess lovers, they were very enthusiasts of this question, and they were trying to solve it, and by trials, after different various trials, they came to a conclusion, and they guessed that the answer is 5. Okay, and later it was this problem was named as the 5 queens problem. And once they knew that the number is 5, they started asking the next question. You have 5 queens in your hand, and how will you place the queens on the chessboard such that all the squares are dominated? Okay, so that comes to the second part of that question. How can one position 5 queens on a chessboard so that they command or occupy every square on the chessboard? And together with this question, they added some conditions also. The condition which they were added was without threatening each other. So they have to place the queens in such a way that the queens do not threaten each other. Okay, and later various type of questions was asked. This adjective was changed without threatening each other. It was changed to some other conditions. The question was like this: how can one position the 5 queens on the chessboard so that they command or occupy every square, and they lie on a central diagonal or the diagonal, they lie on a diagonal line, or they lie on a horizontal line, or they lie on a vertical line, like that. Okay, so they changed the conditions. It was very fun to do that. Each time they get a different answers, and these answers led to these questions, this problem, and the answers to that led to the concept of domination. So let us see. This is how the graph is. The problem is modeled using a graph. Here you have a 8x8 chessboard, and I have put vertices for each square. Okay, and I haven't drawn any edges because drawing all the edges will make this graph very much complicated. But you have the idea which are the edges. The two squares or two vertices here. This vertex is adjacent to all other vertices where the queen can move. Okay, and you know, queen can move in a horizontal direction, vertical direction, and in a diagonal way. Okay, so any number of squares the queen can move. So these are the, so this vertex will be adjacent to all the vertices in this row. It will be adjacent to all the vertices in this row, in this column, and it will be adjacent to all the diagonal vertices also. Okay, so I have not included the edges, but you know the edges now. Now I'm trying to find a solution. I'm trying to place the 5 queens such a way that all the 5 queens will lie on the central diagonal and they dominate every square. So I'll show how to place. So let us place the first queen here. Okay, so I have drawn a red line. The red line shows that all the vertices in this is dominated by the first queen. Okay, so these are the vertices dominated by this first queen. So let us place the second one. Second, I will place it here, and you can see the dominated vertices in the red lines. Okay, and the third one I'm going to place it here. So this you will see, these are the dominated vertices. Now, and the last one I will put it here. Okay, no, fourth one I'll put it here, and the last one I will put it here. So these red vertices are the 5 queens. And what they have done, what we have achieved is placing these 5 queens in the diagonal position. We have dominated all the vertices. Dominated all the vertices means you can see a red line. Every vertex is touched by a red line. That means all the vertices in this chessboard, it is dominated by these 5 queens. Okay, so this is idea how to basic idea of solving the queens problem. So these 5 queens were 8x8 chessboard were done with some other number also, and it was fun to do all these things. But this concept of domination, it started gaining some more importance rather than just a puzzle. The formal definition came with the publication of 2 books. One was by Burge in 1958, and the other was by Orr in 1962. And this concept of domination occurs in wide variety of problems like communication networks, facility location problems, security monitoring systems, and lot many. Okay, and you cannot list it. You cannot find a list for such the applications of domination. Now, additional conditions imposed on the definition led to variations of domination. So there are a lot many variations also for domination. Whenever you impose an additional condition to the basic definition of domination, you will get a variant of domination. Okay, and examples are total domination, connected domination, power domination, Roman domination, and there are Italian domination, secure domination, and many more. Okay. And I think around lots of PhDs are there going on which on this topic itself, domination. So today's lecture, we are going to see what is the basic definition. I'll start from the definition. What's the definition of domination? We will see some examples. We see domination in some classes of graphs. In between, I will give some interesting classes, definitions, some operations or those things, and we will see the interesting results in this area. Okay, and also we will see one variant of domination, that is power domination, which I am interested in. So I will present the definition, examples, and power domination in some classes, and what are the directions of work going on, and some interesting results. Okay, and some of the areas where the research scholars can find results in this can work in future. Okay, this is how I have scheduled my talk. And after the first session, I think we will have a break for, say, 5 minutes, and then go on to the second session. So let us start the first session. We'll start with the basic definition. I hope the definition of a graph, everything is known to us. So this is the 5th day, so all of you may be familiar with graphs. So let us start right away with the definition of a dominating set. A set of vertices D contained in V in a graph G equal to VE, having the property that every vertex V element of V minus D is adjacent to at least one vertex in D. So what is the meaning of that? So D is called a dominating set if D is a subset of V, subset of the vertex set, okay, and you take any vertex of V, any vertex of the graph, you will find that that vertex will be either it belongs to D or it has a neighbor in D. Okay, you take any vertex, it should belong to D or it has a neighbor in D. So if it does not belong to D, it should have a neighbor in D. So that vertex is taken care of by the vertices in D. So that is called a dominating set. Okay, and what is domination number? Domination number, it is noted by gamma G. And gamma G is the cardinality of the smallest domination set in G. Of course, you may have more than one dominating set. And of all the dominating sets, there may be minimal dominating set. Minimal dominating set means if you remove one vertex from that dominating set, it will not dominate the whole graph. Okay, such sets are called minimal dominating set. Of all the minimal dominating set, the one with the minimum cardinality, you will look for the one with the smallest cardinality among the minimal dominating set, and that will be the domination number gamma G. And remember, you may have more than one minimal dominating set, but the cardinality will be the same for the smallest. We are looking for the smallest cardinality. So there is no doubt about the definition gamma G. So you have a dominating set D and the domination number gamma G. And whenever you hear a definition, you should think of examples. Okay. So let us think of this example. Look at this graph. It's just a general graph, and can you look at this graph for 2 seconds and tell me what is the domination number, or can you identify at least one dominating set? Okay, so hope it's clear to you. You can see, you take these three vertices, 1, 3, and 5. They form a dominating set. You can see this vertex can dominate these two. This vertex will dominate this one. This vertex will dominate these two. So it will form a dominating set. And the question is, to say that gamma g equal to 3, we should be very careful. You should check whether any set with the 2 vertices can dominate. So let us check that. Can you take any 2 vertices? Since this is a small graph, the work is easy. You can just to understand. See here, you take if you take these 2 vertices, you can dominate. Of course, you can dominate these 3, but you can't dominate this part. Okay, now if you take 1 and 5, in that case, you can dominate all these vertices, but you cannot dominate 3. The vertex 3 is not dominated. If you take 3 and 5 also, it's not done. Okay, so for this, since this is a very small graph, it can be done by trial and error method, and it is you have. I hope all of you are convinced that gamma g of this graph is 3. Okay. Now, be careful. A graph can have more than one minimum dominating set. I'll give an example for that. See, look at this graph. This is C4, a cycle on 4 vertices. You can see this 2 will form a dominating set. Gamma g is equal to 2, and this also will form a dominating set. And you can't dominate this graph with just single vertex. So gamma g is equal to 2. Okay, so this 2 will form a. So here there are 2 different dominating sets. Also, you can find others also. These 2 will also form a dominating set. Okay, so a graph can have more than one minimum dominating set. Minimum dominating set, you call it as a gamma set. Okay, so it can have more than one minimum dominating set, but there is no ambiguity over the definition because we are taking the cardinality. So cardinality will be the same. We are looking at the smallest cardinality. Okay. Now you have a parameter or you have a graph invariant in your hand, and you have the definition of that. And how will you work with that? Okay, so how to start the work? How the work started in the case of domination number? See, what is gamma g for a general graph? That's the first question which we can ask. Do you have any closed formula for finding out gamma g for a general graph? Now, the first step towards this is to find out where do this gamma lie. If you are given a graph with n vertices, can you find a bound for gamma g? Okay, that's the first thing. That is how you approach the problem. Okay, you want to find a number, but you want to find a number or a gamma g, the graph invariant, and where we want to look for. That's the first thing you should know. So the first thing is to find the bound for gamma g. And obviously, this is a trivial bound, that is 1 less than or equal to gamma g less than or equal to n, where n is the order of the graph. And this bound is very trivial because gamma g is greater than or equal to 1. That's very clear because you know that you need at least one vertex to dominate the graph. So gamma g should be greater than or equal to 1. And what about the other bound, upper bound? You have only n vertices. So if you take all the n vertices, obviously the graph will be dominated. So gamma g should be less than or equal to n. So we have got a bound that is, it is a gamma g is a real number. It's an integer. It's an integer, and it lies between 1 and n, where n is a finite number. So suppose we are looking for only finite graphs. So gamma g will lie between 1 and n. Okay. So there are only finite candidates for gamma g. So what's the problem? So how will you find the gamma g? You will enumerate all the 2 raised to n subsets of vector set in the non-decreasing order of cardinality. So you can see the power dominating set. Dominating set. It is a subset of the vertex set, and if the vertex set has n elements, it's very clear that you can have 2 raised to n subsets. So you enumerate all the 2 raised to n subset. It is a finite number since n is finite. So you enumerate all the 2 raised to n subsets in the non-decreasing order of cardinality and verify for any subset S contained in V whether S is a dominating set. And in that case, you will get finally you will reach a number where it is dominating. Okay, so you are sure to reach a number because the gamma will lie between 1 and n. Okay, so such algorithm is possible. So what's the problem with this algorithm? It takes order of 2 raised to n steps. What does it mean? The time consumed for this algorithm, it is not in terms of a polynomial, it is not a polynomial time algorithm, it is an exponential time algorithm. So such an algorithm has an exponential time complexity in the order of the graph. So if the order is very large, then the time also will be very Yeah. So that means that is not desirable. We need it in a fraction of a second or so. Or we would like to have it like that, but it's not the case. So the problem, so the way of enumerating all the sets won't work. So what is the next question? Is there any faster algorithm? Can you find any faster algorithm for that? That's the next question. But unfortunately, till date, no domination algorithm has complexity better than an exponential time complexity has been constructed. So that's a problem now. So why can't we try for one? Better not, because the problem of finding gamma G is proved to be NP complete. Now, what do you mean by NP complete? Maybe you may be familiar of classes of graphs. The classes of problems, they belong to P, NP, NP hard, NP complete, all those things. What do you mean by, I'm not going into detail, but I can give you just an information that P means a problem belong to the class P means there is a polynomial time algorithm for finding out that solution of that problem. Now, NP means it is not likely to have a polynomial time algorithm. I don't say that it will not have any polynomial time algorithm, but I can say it is not likely to have a polynomial time algorithm. So this gamma G is proved to belong to this class, NP complete. Okay, so there is no use of. I think it will be very tiring effort to find a polynomial time algorithm. So it may not work. Okay, so now how will you go further? Now you have a parameter and you are trying to find the bounds. You got the bounds, but you don't have you are not reaching a polynomial time algorithm, and so again we are in a bad situation. So how will you move further? So the next question is, can we improve the bounds? So that's another way of attacking the problem. Okay, is the bound tight? That is another question which you can ask. What do you mean by asking, is the bound tight? That means, is the bound attained for some classes of graphs? If the bounds are attained, it means that you cannot improve it further without imposing some, without restricting ourselves to some subclasses. Okay, so if the bounds are attained, you can't go further without restricting ourselves. So the next question is, can we find closed formula for any class of graphs, any subclass? Okay, not in general. Can you find a closed formula for any subclass? Now look at this. Look at this family. You have a class of graphs here. You have a complete graph with this is a complete graph K4, and I have put a red vertex here to show that this will dominate the whole graph. Here, this family is called stars. Here also I have a universal vertex. This family is called wheels. Here also I have a universal vertex, and this family is called fan. Here also I have a universal vertex. So these are some of the families which for which gamma G equal to 1. For all these families, they have the specialty that they have the domination number is equal to 1. And what is common in all these families, they have a universal vertex. So you can, that is one way of doing. You can fix the parameter, say gamma equal to 1, and look for all the families having gamma equal to 1. This is one way of doing. And the other way you can turn it around, that is, you can fix the families now. You can fix to some subclasses, say for gamma, what is gamma of Cn, cycles, what is gamma of Pn. That is also one way to attack this problem. So gamma of Cn is ceiling of n by 3. Gamma of Pn is ceiling of n by 3. And you can see this is an example. This is P8, path on 8 vertices. And you can see 8 by 3, it was 2 point something, the ceiling will be 3. So this will these 3 red vertices will dominate the graph. Okay, and similarly for cycle, this here again the domination number, it is C8, so it is the domination number, you have 3 again. So this is a way of doing it, that is you fix the class and look for the closed formula in that class. Now we have seen that you have a parameter and you are not able to catch hold of that parameter in general. So we are looking for bounds, we are looking for subclasses, all those things. So I'll in the next session I will I will show you some of the bounds which have already been worked out, so that whenever you get a new parameter, you will get an idea how to do this. Okay, so all these things is done for domination number, so don't need to try for domination number. You can try for some other variants of that. Okay, so this, you look at the this bound closely, 1 less than or equal to gamma g less than or equal to n. Here the lower bound is attained for graphs with universal vertex that we have seen examples, and upper bound is attained for totally disconnected graphs. So you can see that the lower bound and upper bound is attained here. That means you cannot improve further. Seems that the bound can't be improved in general, so restrict ourselves to subclasses. So let us restrict ourselves to subclasses, and that was exactly what was done by Orr in 1962. Their group they came up with a improvement of this bound. That is, if G is a graph with no isolated vertices, then gamma G less than or equal to n by 2. So originally the bound was gamma G less than or equal to n. Now it is improved to gamma G is less than or equal to n by 2. And what was the cost of this? He had to impose a condition, no isolated vertices. But that condition, no isolated vertices, is not a stringent condition. It is an attainable condition. So there is no problem with this bound. It is interesting bound. Okay, now let us improve. Can we improve further? The next question is, once you get a bound, can we improve it further? Okay, this bound is also attained. So that is the specialty of this bound. This is also attained for some family. To say what about this family, we have to define an operator, and that operator is known as corona of G and H, G corona H, G circle H. And don't worry, it has nothing to do with COVID-19. So no, don't need to worry about that. This is just a graph operator. So let us see what is that. G corona H is a graph formed from one copy of G and more G copies of H, where ith vertex of G is adjacent to every vertex of the ith copy of H. So it's very interesting to once you read the definition, you may not be clear. So let us take an example. Let us see how to draw the corona graph. Okay. So here I have taken K2 corona K2. So how will I draw K2 corona K2? I will take one copy of G. That means one copy of K2. So this is the copy which I have taken, blue copy. Okay. Then I have to take mod G copies of H. That means mod G is equal to 2 here. So I take 2 copies of H. H is K2 here again. So I take two other copies of K2. So I take here yellow copies. Okay. Now what to do? Where the ith vertex of G is adjacent to every vertex of the ith copy of H. So the first vertex of G is adjacent to all the vertices of the first copy of H. Okay. Here the second vertex is adjacent to the second copy of H. So you get, this is what you get, K2 corona K2. So I have just drawn with dotted lines just to show that this is the graph which I have, this is the edge which I have joined to form the corona. Okay, so this graph is K2 corona K2. Now, this class is a very, this operator is very important in terms of domination, and in terms of power domination also it plays a very important role. So let us see some more detail. If you have a pen and paper, you can just work out what is K3 corona K2. What is that? You have a K3, you take a K3, you take a K3, and for each vertex of K3, you put a copy of K2 here, you put a copy of K2 here, another copy here, and make them adjacent. So this will be K3 corona K2. Is that clear? And if you work out, if you take a pen and paper and just try to draw it once, it will be clear. Okay. Now one more class, it is interesting for us, so I'll explain that also. They are called caterpillars. What are caterpillars? Caterpillars are PM corona KN bar. Kn bar means Kn complement. PM corona Kn bar. So here I have drawn P4 corona K2 complement. So I take one copy of P4 and 4 copies of K2 complement, okay, and make them adjacent here, okay. So this graph is called a caterpillar. Actually, caterpillars are PM corona Kn complement, okay. Or another way of defining caterpillar is a caterpillar is a graph whose removal of the pendant vertices will end up with a path. Such a graph is called caterpillar. Caterpillars are very interesting class. We have a lot of examples and counter examples from this class. So that's why I want to introduce this class. Okay, so this is one caterpillar, P4 corona K2 complement. Okay. Now, what does this corona has to do with this bound, our bound? So this is the result. That is gamma of H corona K1, which is equal to N by 2, where N is the order of H corona K1. Okay. Order of H corona K1 is equal to N. Now, I have taken it for an example, gamma of P4 corona K1. I have taken P4 and corona K1 means you have to attach pendant vertex. Okay, K1 means only single vertex. So you have to attach vertices here. So this is P4 corona K1, and the domination number is you should take all the 4 vertices to dominate. That's clear. And what is the order of this graph? Order of this graph is 8 and domination number is 4. So which is exactly 8 by 2. Okay. So for this class, gamma of for this class H corona K1, this bound is attained. Okay, this bound is attained. So this result, this is one class, and actually characterization of graphs for which this bound is attained, it was done by 2 groups. First one was by Payen and Swang in 1982, and later by Fink, Jacobson, Kuich, and Roberts in 1985. They did it independently, and the characterization goes like this. For any graph G with even order n and no isolated vertices, gamma G equal to n by 2 if and only if the components of G are cycles C4 or corona H corona K1 for any connected graph H. Okay, so if G has even order, why should you put this condition even order? Because gamma G is an integer, so n by 2 to be an integer, n should be even number. So that is why this condition is there. And it is equal to gamma G equal to n by 2 if and only if the components of G are of this type, that is C4, either it should be C4 or it should be of the form H corona K1 for some connected graph H. Okay, so this was the characterization of the family which attained the bound. Later, many attempts were made to improve the bound. Many works were done on this bound. So if you are interested, I can give you the references and you can read further. Okay, let us move on to another bound. Okay, bound in terms of order and degree. So this is another bound for any graph G, ceiling of n by 1 plus delta G is less than or equal to gamma G less than or equal to n minus delta G. This bound, here n is the order of the graph and delta G is this is capital delta, it is the maximum degree of the graph, okay, of any vertex. So this upper bound is this upper bound is was done by Birch in 1962 itself, but the lower bound, it is attributed to Valikar, Acharya, and Sampat Kumar in 1979. See the difference. Okay, so a lot of work has been going on in this area since from 1962 to get the upper bound was found in 1962, and to get the lower bound we had to wait some more years, right? Okay, now is this bound attained? The next question, whenever you get a bound, the next question you should ask is the bound attained? Is the bound tight? So you can see that for this class, Kp corona K1, again corona come into picture. Kp corona K1 means it is a complete graph on P vertices, and corona K1 means you have to attach pendant vertex to every vertex of that. Okay, so what is the order of that graph? Kp corona K1, Kp will have P vertices, and you are attaching again and one pendant vertex to each of the vertex, so the order will be 2p. Okay, Then what will be the maximum degree? You know that Kp is a p minus 1 regular graph, and you are attaching one more vertex means it will become a p regular graph. So it is the maximum degree is p. So n minus delta is 2p minus p, which is equal to p, and it is shown that gamma of Kp corona K1 is equal to p. So here this bound is attained. Okay. Now, this is one family. Can we characterize graphs which attains this bound? Can you find all the graphs which attains the bound? It is not done in general, but it is characterized in trees. In trees, it is characterized. For that, to say what is the characterization in trees, we need 3 definitions. So these definitions are very important definitions which you can make use of in some other areas also. Okay. So that's why I'm explaining the definitions again and again. Subdivision of an edge. Subdivision of an edge UV is obtained by removing the edge and adding a new vertex W and the edges UW and VW. So subdividing an edge, it simply means putting a vertex in between that edge. Okay. So I'll show examples. Before that, let me say 2 more definitions. The first definition, spider. Spider is a graph obtained by subdividing edges of K1n. And originally, it was defined as subdividing edges of K1n exactly once. And later it was the definition was slightly modified, and whenever the edges are subdivided any number of times, you call it as a spider itself. But originally it was defined like this. A spider is a graph obtained by subdividing the edges of K1n exactly once. And another definition is wounded spider. Wounded spider is a graph formed by subdividing at most t minus 1 edges of a star K1 t for t greater than or equal to 1. You know that, I hope you know this notation is for the stars. It is a complete bipartite graph with one vertex in the first set and t vertices on the other set. Okay, so these are called stars. So if you subdivide all the edges except at least one, okay, if you at least one must not be subdivided, such a graph is called wounded spider. Okay, so let us see examples. So this is star K18. Okay, K18, and you have subdivided the edges. That means you have introduced new vertices here. So these blue vertices are the ones which I have introduced. So this is a spider, and you can see why it is called a spider, right? See, actually, this is not only for K18. You can do it for any star K1n, but since it is a spider, I do it for K18. Okay. Now, why it is called wounded spider? This one is called wounded spider. Wounded spider means at least one edge is not subdivided. Here you have 3 edges which are not subdivided, and you can see why the name comes. It looks like a spider with a wounded leg. Okay, so this is a wounded spider. So hope the definition it plays important role in domination as well as power domination, in partition of trees, all those things. Trees have spider partition, all those things. Spider is a very important, very interesting class of graphs. Now the characterization goes like this. For any tree T, gamma t equal to n minus delta t, that is it attains the bound if and only if t is a wounded spider. Only for wounded spiders it attains the bounds, and this was done by Domke, Dunbar and Marcus in 1998. Then coming to that was all about that bound in terms of degree and the order. And later lots of work has been done, and if you search the literature, you can find more interesting results on that bound. Now I am going to introduce one more bound. Just to give you information about this, bounds in terms of degree, diameter and girth. I am not going into the details of the bound. I'll just list some of the bounds, and if you are interested, I can give you the references and you can work out. And for this, you need some more definitions. Maybe these definitions may be familiar. Some of you may be new to it. So I am just stating the definitions. Eccentricity of a vertex, E of V. E of V means it is a maximum d of uv such that u is a vertex of G. So that is the distance. You take a vertex and you calculate the distance. So it should be, since it is a distance, it should be a connected graph, of course, and you should calculate the sorry, you should calculate the distance from that vertex to all the other vertices and look for the maximum distance, and that will be the eccentricity. And radius is the minimum eccentricity, diameter is the maximum eccentricity, girth is the length of the smallest induced cycle in a graph, circumference is the length of the largest induced cycle in a graph. And these are some definitions which will be very useful. So let us see one example also. Look at this graph. I have written down some numbers over here. These numbers are their eccentricities. So look at this vertex. It has eccentricity 3. Why it has eccentricity 3? You look for the distance of this vertex with the other vertices. With this vertex, the distance is 1. With this vertex, the distance is 2. And with this vertex, it is 3. So this is the farthest vertex with respect to this one. Okay, so length of that path will be 3, and so eccentricity will be of this vertex will be 3. Similarly, you can look for all the vertices and the distances, and you can see that the eccentricity of this vertex is 2, and I have written down all the eccentricities. Now, what is radius of this graph? Radius is minimum eccentricity. Minimum eccentricity here, it is 2. So radius is equal to 2. Now, what about the diameter? Diameter is maximum eccentricity. So what is maximum eccentricity? Here, the maximum eccentricity is 3. So diameter equal to 3. Now, girth means the length of the smallest induced cycle. So here the smallest cycle is K3. So you have a C3 here. Okay. So the length of that cycle is 3. So girth is equal to 3. And circumference is the length of the largest induced cycle, and the largest induced cycle here is 4. So it is 4. So you may have a doubt. See, I have a cycle here 5 cycle. So why the girth circumference is not equal to 5? Because the definition is circumference is length of the largest induced cycle. What do you mean by induced cycle? Induced cycle means it will not have any chords. See here, this is a cycle of length 5, but you have a chord in between. So these chords are not allowed in induced cycle. So it is the largest induced cycle is C4, and so circumference is 4 here. And there is a warning in graphs, diameter need not be twice the radius. It's interesting to note that here diameter is 3 and radius is 2. It's not twice the radius. It need not be always. Okay, so this is the basic definition. So let us, I'm going to list the bounds here. I'm not going to detail it. Lots of work are done in this direction also. If a graph has diameter g equal to 2, then gamma g less than or equal to delta g, where this small delta represents the minimum degree of the graph. For any connected graph G, if girth is greater than or equal to 5, then gamma G is greater than or equal to delta G. If girth is greater than or equal to 6, then gamma G is greater than or equal to 2 into delta G minus 1. If graph G has delta G greater than or equal to 2 and G of G greater than or equal to 7, then gamma G greater than or equal to delta G. If G is planar with a diameter G equal to 2, then gamma G less than or equal to 3. And if G is planar with a diameter G equal to 3, gamma G less than or equal to 10. So you can see so many bounds are there, and you can see for each bound you have put some conditions here. Okay, here there is a condition of planarity, and here diameter there is a condition, and for whenever these conditions change, you can see the bounds are also changing. So a lot of work is done in this direction. So if you are interested, you can carry on. You can find interesting problems in this area also. Now, coming to another important direction of work, that is any talk on domination cannot skip a famous topic called Wissing's conjecture. Now, coming to Wissing's conjecture, before that we need some definitions. So another idea of doing work is what is studying the effect of graph operations on gamma. That is, what will happen to gamma when some graph operations are done? See, we have seen one operation already. There are various graph operations. One of them which we have seen already, corona, is a graph operation. Likewise, there are many other graph operations. You can have join of two graphs, union of two graphs, product of two graphs. And in product itself, you have various types of products. Cartesian product is there, direct product is there, the strong product, and so on. Okay. Now, what will happen to the parameter gamma when these operations are done? That's an interesting area. Now, I'll just define what is Cartesian product. Cartesian product of G, this is it is written as G box H. Okay, G box H. So it is another graph. Now, what is that vertex set of that graph? Vertex set of G box H is the Cartesian product of vertex G cross vertex H. That is the you consider V of G and V of H as sets and take the Cartesian product. So the vertices are ordered pairs. Okay, since it is a Cartesian product, the vertices are ordered pairs. Now, two vertices GH and G dash H dash are adjacent in G box H if they are equal in one coordinate and adjacent in the other. Okay, that is, if one of the coordinates are equal and the other one they are adjacent, you make the adjacency in G box H. I will show examples so to make it clear. Before that, let me define some classes. Pn box PM, it is called Pn Cartesian product PM is called n by m grid graph. This is very important. You will see it, you need it for the next session also. So please remember this name. And Pn box Cm, they are called cylinders, n by m cylinder. And Cn box Cm, they are called tori. Okay, so these are some interesting classes which we need. Okay, so let us see in detail what is a box product. Okay, so take an example. I want to draw P4 box P4. So what to do is you take 4 copies of P4. So this box product, you have horizontal copies and vertical copies. Okay, you have vertical copies of P4 and horizontal copies of P4. So you take 4 copies here. Now, where does this 4 comes from? It is the cardinality of the second graph. Okay, so P4 has 4 vertices. So I take 4 copies vertically of the first graph. Okay, P4. So P4, you have 4 copies, and you have you form copy of the second graph using the vertices horizontally. So you with these horizontal vertices, you draw a P4. The second graph, second copy is like this, and third copy is like this, and fourth copy is this. So this will form P4 box P4. So it's easy to draw. Easy to draw the Cartesian product if you understand it like this. This horizontal. You have horizontal copies and vertical copies. It can be either way. There is no which one you should take horizontally. There is no restriction on that. You can take any one, but you should understand G box H as horizontal copies of G and vertical copies of H, or vertical copies of G and horizontal copies of H, like that. Okay, so I have taken here, this is you have vertical copies of the first graph and horizontal copies of the second graph. Okay, so this is P4 box P4. Okay, now let us see what is P4 box C4. Again, I take vertical copies here, P4, and with the horizontal vertices, I form a C4. Okay, here I have formed C4. So you have horizontal copies of C4. They are called C4 fibers in this graph. Okay, so this is P4 box C4. So this is a cylinder. Okay, you can imagine why it is called a cylinder. Now, this is C4 box C4. C4 means horizontally you should take, vertically also you should take C4, and horizontally also you should take C4. So you have these are the vertical fibers of C4, and these are the horizontal fibers of C4. This is how you should understand the Cartesian product. Okay, and only if you understand it like this, it will be easier to work with this. Now, what is Wissing's conjecture? Wissing's conjecture, it was proposed in 1968. It goes like this: gamma of G box H is greater than or equal to gamma G into gamma H. So this is a conjecture. It is very interesting conjecture. Attacks were there on this conjecture from various directions. Once this conjecture was put, there were a lot of work in this direction. It was attacked from various directions, but still it is open, and I don't know when it will be solved. And if you want to have a if you want to know the story of this conjecture, you can refer this paper by Bosdem Besar. It appeared in Journal of Graph Theory. Wissing's conjecture, a survey and recent results in 2011, and up to 2011 everything is written in this paper, and after 2011 also a lot of work is done in Wissing's conjecture. It is open means it is not proved in general, and also it is not disproved also. That's the thing. So attempts were made to prove such results for other graph problems. Since we are not able to, nobody is able to solve this conjecture, so they were trying to look at other variants of this conjecture. So what will happen? Do you have such a thing for other graph products also? That is that's another direction of work in this area. Then studies on Wissing-like conjectures on other parameters. There were studies on other parameters like chromatic number or some other parameter you have. Whenever you have a parameter, you look whether Wissing-like conjecture is holds in that parameter, for that parameter. So that is one way of one direction of research. Attempts were also made to find domination number on or bounds on domination number of Cartesian product of specified graphs. So if it is not proved in general, whether there were attempts to prove it for certain classes of graphs. Some of them fixed the graph G and tried to vary H or something like that. Or some of them tried to improve the bound. Like that, work is still going on. And these are some of the results, exact results which you got. Gamma of P1 box Pk is ceiling floor of k plus 2 by 3 with k greater than equal to 1. Here the first graph is fixed. Then gamma of P2 box Pk, it is also k plus 2, floor of k plus 2 by 2, k greater than equal to 1. Here also the first graph is fixed. And for larger values, some bounds are there, and I have not included that in this. If you want, I can give you the references. And this graph, this parameter gamma of tori, Cn box Cm, they are also extensively studied. So Wissing's conjecture, many attempts have been made to try to improve the situation by improving the bound or restricting to some classes. Works are going on like that, and there are some works in the other direction also. They trying to disprove the conjecture, and we are waiting for something. And if anyone is interested, can try. Now, I would like to end the first session by talking one more area of idea of research, that is changing and unchanging domination or fault tolerance. An important consideration in the topological design of a network is fault tolerance. What do you mean by fault tolerance? That is the ability of the network to provide service even when it contains a faulty component or components. So if you have a network, some of the if it's a communication network, if suppose something happens to one of the nodes, what will happen to the network? Okay, whether it will work efficiently. Okay, so that such type of thing, that is called fault tolerance of a network. The behavior of a network in the presence of a fault is analyzed by determining the effect of removing an edge or vertex. Studying the effect on gamma G when G is modified by deleting a vertex, deleting or adding an edge is an attempt in that direction. This was carried out by Carrington, Harare, and Haynes in 1991, and still the works are going on in this direction. And this group, Carrington, Harare, and Haynes, they studied 6 classes. They have identified 6 classes, and to study this, to study the fault tolerance of a network. And to describe the 6 classes, I need some notations. The notations are: G minus V denote the graph with V, the vertex V is removed. G minus E is the graph with E removed. C means changing, and U means unchanging. V means vertex, E means edge, R means removal, and A means addition. Now, with these notations, this team, Carrington, Harare, and Haynes, they have identified 6 classes of graphs. The first class is CVR. CVR means changing vertex removal. So when we change the when we remove the vertex, the domination number is changed. So gamma of G minus V not equal to gamma G. It is changed for all V element of V. So this is a class like that. Okay. The second class is CER. CER means changing edge removal. So gamma of G minus E not equal to gamma G for all E element of E. This is another class. Then the third class is CEA. CEA is gamma of G plus E were not equal to gamma G. That is also changed. Where when you add a vertex, when you add an edge, and that edge comes from the complement of that graph. Okay. Now UVR means unchanging vertex removal. So gamma G minus V is equal to gamma G. The domination number is not changed. So that is why it is put UVR, unchanging vertex removal for all. This should happen for all vertex. Okay. UER, that is gamma of G minus E equal to gamma G. That is when you remove an edge, remove any edge, domination number is not changing. Then the last one is UEA, that is gamma of G plus E is equal to gamma G for E element of the G complement. So these are the 6 classes which was identified by the team, Harare, Carrington, and et al. And a lot of work has been done in this class, and still there are some scope for work. And it is interesting to study what will happen to domination number when vertex is removed, when edge is removed, when edge is added, something like that. And it will be interesting to what will happen, what is the situation when we move on to some other variants of domination, like connected domination, paired domination, total domination, all those things. What will happen when vertex is removed, what will happen when edge is removed, what about these classes for those parameters. Okay. So these are the main directions of research in the some of the directions of research in the area of domination. And that will like that we have come to an end to the first session of the talk. And I think I need a 5 minutes break so that I will move on to the next topic after 5 minutes. Okay, welcome back. Excuse me, Danya, can I start again?
Yes, ma'am.
Okay. So can you see the screen? It's okay? Is it okay?
Yes, ma'am. Yes, ma'am.
Okay. Okay.
You can make
So
it
in the okay. Okay. Now, in the second session, we are trying to discuss a problem which is a variant of domination in which occurred in electric engineering people. With some people has had some problem with this monitoring power networks. Okay. So it is called power dominating set problem. It is an electrical network problem. It arose in the context of monitoring electric power network. Now, what is an electric power network? Electric power network means it has nodes, edges, generators, loads, etc. And to monitor the network means we should measure the all the state variables of the network. Now, what do you mean by state variables? We need to measure the voltage at a node and the current passing through the edges connected to the nodes. And this is usually done by placing phase measurement units, PMUs, at selected network locations. And this PMUs are a device which can measure the voltage at a node and also current passing through the edges connected to that node. The thing is that PMU is a very efficient device, but it can measure voltage as well as current, at voltage at the node and the current passing through that node. But the thing is that PMUs are very expensive. So the PMUs are expensive devices. Hence, our goal is to minimize the number of PMUs such that the whole system is monitored. So if you are having a network with say 100 or 1,000 nodes, placing PMU at every node is not practical. So we need to we need to find places where we have to locate places where these PMUs are to be placed such that the whole system is monitored. Okay. If you know the voltage, we have advantage in the domination situation. We have only thing is that you have a vertex, or that vertex will dominate all the vertices adjacent to it. You have only one rule there, domination rule. But in case of this, in the electrical network problem, we have apart from that, we have one more rule, that is Kirchhoff's law is there. So we have two basic laws of this electrical networks, that is Ohm's law and Kirchhoff's law. What is Ohm's law? Ohm's law says that V is equal to IR, voltage is equal to current into resistance. Okay. Now, if we know the voltage at a vertex, we can compute the current through the incident edges by Ohm's law, since the resistance is known. But resistance, it's a property of the material with which that wire is made. So you don't need to worry about resistance. That is a known, that can be assumed to be known. So the only thing is that what is the voltage and current. So once you know the voltage, you can know the current. V equal to IR is the equation. So Ohm's law is there. Once you know the voltage, you can calculate the current. That means we need to monitor the vertices only. Okay, so we need to know the voltage only. So knowing the voltage means monitor the vertices only. The edges can be done by Ohm's law. So we need to monitor the vertices. That's our problem now. Now we have one more law, that is Kirchhoff's law. What is Kirchhoff's law? Kirchhoff's law states that in a node, the total inflow is equal to the total outflow. The total current is 0. Okay. So inflow should be equal to outflow. So at a node, the total current will be 0. So that using that law, you can suppose if PMU readings are synchronized via GPS, it is possible to use Kirchhoff's law to calculate the current. Suppose you have a vertex and you know the current through all the edges incident to that vertex except one. then you can very well calculate that one also using Kirchhoff's law. So these two laws, we are at an advantage. We are in a better situation than domination. So we have two laws. So we have actually a variant of domination. So the locations where PMU are placed is critical in the sense that the network must be fully monitored and the cost of monitoring must be minimized. So what is PMU placing problem? Let us formulate it. It is given an electric network. Excuse me, is there any problem? Someone has some. Okay. So given an electric network, find the locations where PMUs must be placed to monitor the entire network using the minimum number of PMUs possible. So this is the formulated, this is the problem, PMU placing problem. PMU pricing problem came from engineering part. It was a problem in electrical engineers, and it was actually modeled by using graph theoretical techniques, and it is equivalent to the power domination problem in graph theory. So let us see what is power domination problem. Now, given a graph, find the set of vertices with a minimum cardinality that can power dominate the entire graph after the iterated applications of certain rules. Now, what are these certain rules? These certain rules come from the two laws which we have, Ohm's law and Kirchhoff's law. Okay, so let us write that the rules are defined so that placing a PMU at a vertex of the power dominating set suffices to monitor the power network. Okay, so the first rule, rule 1, is the domination rule. What is that rule? This rule says that a vertex power dominate itself and its neighbors. Now, what does it mean? If you put a PMU at a vertex, it can find the voltage at that vertex, and also it can find the current passing through all the incident edges. Also, if you have Ohm's law in hand, so if you know the current through an edge, you can find the voltage at the voltage of that neighbor. Okay, so what we have achieved is putting a PMU at a vertex, you can find the voltage at that vertex and also the neighboring vertices also. Okay, so that is called a domination rule. A vertex power dominates itself and its neighbors. And rule 2 is a propagation rule. It comes from Kirchhoff's law. What is that rule? Says that if a power dominated vertex V has exactly one non-power dominated neighbor U, then V also power dominates U. That is, you have a vertex which is power dominated already, okay, and by placing some PMU or by propagation or by domination rule. Now look at that vertex. That vertex has the situation is that it has some neighbors, and all its neighbors are already power dominated except one. So in that case, you can use Kirchhoff's law and find the voltage at that non-dominated vertex also. So that rule is called the propagation rule. So we have two rules for power domination. You have the usual domination rule, and also you have the propagation rule, which comes from Kirchhoff's law. Okay, propagation rule is iteratively applied until it produces no new power dominated vertices. Now, let us say the formal definition of a power dominating set. A set P is a power dominating set if P monitors all the vertices of G by domination and propagation. Okay, so such a set is called a power dominating set. And of course, the parameter, that is the invariant, the power domination number, it is denoted by gamma suffix PG, gamma PG. It is the cardinality of the smallest PDS in the power. The cardinality of the smallest PDS in G is called the power domination number, gamma PG. So as usual, as in the case of domination, you will look for all the power dominating sets, and of all the power dominating set, the one which with a minimum, you will get a minimum power dominating set, and you will look for the cardinality of that. That will be the power domination number. Okay. Now let us take the same example which we have done for domination. Okay, and do you remember? I hope you remember that the domination number of this graph was 3. Okay, so now let us check what is the power domination number. For that, let us I am going to place a PMU at this at this vertex 3. I am placing a PMU here. What will this PMU do? This PMU will measure the voltage at this vertex, and also it measures the voltage at the neighbors also. So it will, this one is also measured, this. Okay. So this vertex, this PMU will monitor itself and its neighbors. Okay. Now, can you improve it further? You look at this vertex, it is a power dominated vertex. You can apply propagation rule. What is propagation rule? If you have a vertex which is power dominated and all its neighbors except one, so this vertex has neighbors, two neighbors, and one of them is already power dominated and only one is not power dominated. If this is the situation, then this vertex can dominate this one also by Kirchhoff's law. Okay, so this here the same thing happened here also. This vertex has two neighbors, one of them is already power dominated, so only one more is remaining. So this can be, this vertex 4 can power dominate vertex 5, so by propagation. So the situation is it is also power dominated. Can you propagate further? Now from here, can you propagate? No. Why? Because this vertex has three neighbors and only one of them is monitored and the other two, there are two which is not monitored, so you cannot propagate further. So you have to place one more PMU. So let us place it here. So when you place the PMU here, it will monitor these two. So the power domination number gamma PG of this graph is equal to 2. And you cannot monitor with one. It's clear, since it is a small graph, it's clear that it cannot monitor with a single vertex. So this is gamma G equal to 2. So this problem, the problem of PMU placing locations, was first posed by Baldwin et al. In 1991 in the journal IEEE. It was a Journal of Electrical Engineers. So it was posed in that journal. In that paper, in one paper, they posed the problem of placing PMU placing locations. And later, this problem was modeled using graph theory techniques by Haynes et al. In 2002. And in Haynes, they what they did was they defined gamma PG using the rules, the domination rule and the propagation rule. They modeled it using the graph theory techniques. Okay, they also gave a bound for gamma PG. And also proved that the problem of finding gamma PG is again NP complete. So this again, we are not in a good situation. This problem is also NP complete, so no need to look for any closed formula in general, but you can try for formulas in certain classes or something. You can do something to improve the bounds. Now let us look for the bound. The bound given was 1 less than or equal to gamma PG less than or equal to gamma G. You can the bound is trivial. The gamma PG greater than or equal to 1, it's okay, because you need at least one vertex, at least one PMU is needed to monitor a network. So this bound is trivial. And what about this bound? Gamma PG is less than or equal to gamma G. You see, gamma G, what does gamma G do? The vertices in gamma G, the gamma set will dominate all the other vertices, right? So here you have they will directly dominate without any propagation. So you have propagation also. So this gamma PG will be less than, you need lesser vertices than gamma G. So gamma PG is less than or equal to gamma G. So this was the bound, and we are trying to improve it. Okay. Now the next question, the same question we are going to ask is, are the bounds attained? Yes. You have the graph gamma P of Kn equal to 1. So this is a complete graph. So it is equal to 1. Then what about the upper bound? You can see that. Okay, here this is gamma, it's gamma P, it's not gamma, it was a mistake. Okay, gamma P of Pn corona K2, it is equal to N. You can, so this is Pn corona, P5 corona K2. P5 means you have path on 5 vertices, and you have K2 here. For each vertex, you have a K2. You join those vertices. This will form P5 corona K2. And you need all these five vertices to power dominate it. So gamma P of P5 corona K2 is equal to 5. And also it can be shown that gamma of P5 corona K2 is also equal to 5. So these are two classes where the bounds are attained. Okay, do you have these are examples of classes where bounds are attained. So are there other families which attains the bounds? That's the next question. So you have identified one family. So you understood that the bound is tight. Okay, so are there any other families? Yes, there are other families. You can see gamma p of k1n. What is that? Star already have universal vertex. So gamma is equal to 1. So gamma p is also equal to 1. For wheels also the same case. Fan also the same case. And this, let it be there. I'll come to that later. So these are some other families for which gamma p equal to 1. So you can say that all graphs with gamma equal to 1 also have gamma p equal to 1. So if gamma is equal to 1, then gamma p is obviously it should be equal to 1. So we are not interested in such graphs. So let us see whether there are graphs with gamma not equal to 1 but gamma p equal to 1. So this is such a candidate, gamma p of k2n. K2n means 2. I haven't drawn the graph. You have two vertices here. It is complete bipartite graph. N vertices here. All the vertices in this partition is adjacent to all the vertices here. So you can take just one single vertex from this partition. It will dominate all the vertices here, and the remaining vertex in the first partition can be dominated by propagation. Okay. So this is one such candidate. So you are interested in graphs with gamma not equal to 1, but gamma p equal to 1. And you have another example, path. P8. You have seen that P8 is 3. Gamma of P8 is 3. And you can, from here, you can see that gamma P of P8 is equal to 1. You need any one vertex. You put a PMU here, then it will dominate the neighboring vertices. And this domination goes on like this because all the vertices are of degree 2. So there is no problem. So for any path, gamma P is equal to 1. Similarly, like any cycle, gamma P equal to 1. So you have so many classes with a gamma not equal to 1 and gamma P equal to 1. So here you have degree 2 vertices, and you see the propagation is going on since there are degree 2 vertices. But one may have a feel that degree 2 vertices has nothing to do with gamma P. It's not that's not the case. Degree 2 vertices play important role in gamma P. Okay, it's not necessarily true that if G dash is a graph obtained from G by subdividing one edge, then gamma P G dash is equal to gamma G. It is not true. That is, if it's a homeomorphic copy, this gamma P need not be equal to. So you can see here you see this example. This is a graph with a gamma P equal to 2. These two are the vertices, PDS. This will form a PDS. And you have subdivided this edge. Okay, I put a vertex here. Now, this is a degree 2 vertex. Okay, I have introduced a degree 2 vertex here. But then what happened to gamma P of T dash? It is increased to 3. So degree 2 vertices, it has something to do with gamma P. Okay, so don't say that if whenever you see a degree 2 vertex, you can just ignore it. No. Now coming back to the bound 1 less than or equal to gamma pg less than or equal to gamma g. Now looking at this bound closer, it will be interesting to study the difference of gamma g minus gamma pg. What's the difference? What is this difference? Gamma g minus gamma pg. Is it bounded, or is it a constant, or is it arbitrarily large, or can you make it arbitrarily large? That is that's the type of question which you can ask. Okay, is it bounded? Difference? Actually, the result is that gamma g minus gamma pg is arbitrarily large. What is the meaning of saying that? Given any n, I can give you a graph with gamma g equal to gamma g minus gamma pg equal to n. Okay, so this difference is arbitrarily large, so you cannot do something. We cannot improve there is something over here in this interval. Okay, so look at this graph, this class, gamma of k1n corona k1. Again, corona comes into picture. Gamma of k1 and corona k1, and this has the domination number. It's not gamma, it's gamma p. Okay, so domination gamma is n plus 1 and gamma p is equal to 1. So that is the case. So here you have gamma is equal to n plus 1 and gamma p equal to 1. Look at this example, gamma of K14 corona K1. K14 means you have one vertex here and you have 4 adjacent for pendant vertices, and corona K1 means you have to add, excuse me. Yes? Excuse me? Is there any problem? Someone has unmuted?
No problem, ma'am.
Okay, okay. Then, so this is K1n. So K14, you have a central vertex and you have four pendant vertices, and you have to take corona with K1. So that you have to take attach pendant vertices to every vertex here. Okay, so I have attached pendant vertices, and for this vertex also I have attached a pendant vertex. Now you can see gamma of this graph is 5. The domination number is 5. You need this vertex and all the pendant vertices, any of that. You need 5 vertices to dominate it, but to power dominate it you need only just single vertex. Okay, so the thing is that given any n, I can give you a graph such that gamma g minus gamma pg equal to n. That means the difference gamma g and gamma pg is arbitrarily large. Can be arbitrarily large. For any n, I can produce a graph like that. So it's interesting to study this difference. So the next type of question is, can we characterize graphs with gamma pg equal to 1? So we have already seen that for all graphs with gamma equal to 1, we have gamma pg also equal to 1. But we have identified some classes where gamma not equal to 1, but gamma pg equal to 1. So it's a larger class, gamma pg equal to 1. So can we characterize it? Okay. So this is done for trees. And the characterization is like this: for any tree T, gamma pt equal to 1 if and only if T is a spider. Okay, spider which we have defined earlier. This was done by Haynes and the group in 2002. The next question is, can we characterize graphs with gamma pg equal to gamma g? So this is a very interesting question. And what's the direction? What's done in this area is, Haynes and et al. In 2002, they proved that the class of graphs with gamma pg equal to gamma g does not admit forbidden subgraph characterization. Now, what do you mean by forbidden subgraph characterization? So for that, I'll come to the next slide, and then we'll go back. Okay, now what do you mean by forbidden subgraph characterization? So whenever we try to characterize a graph, what do you mean by characterizing a graph? By characterization of a class, we mean if you know the characterization, you can given a graph, you can say whether that graph belong to that class or not. Okay, so there are different types of characterizations. One of them is forbidden subgraph characterization. Then there are cross type characterizations, or listing the conditions or something like that. There are different types of characterization, and one famous type is forbidden subgraph characterization, that which we use it's very familiar type of characterization. Now, what does it say? It is characterizing class of graphs by listing a set of forbidden subgraph. So in this type, what we do is we will list a set of graphs which is forbidden for this class. Okay, the very famous example is, a graph is bipartite if and only if it does not contain any odd cycles. Now, so how will you identify a bipartite graph? You will look whether it has any odd cycle. If you don't have any odd cycle, then it is bipartite. Otherwise, it's not bipartite. Okay, so here the forbidden graphs, what is that? It is odd cycle. Odd cycles are forbidden. So this type of characterization is called forbidden subgraph characterization. There are certain other class also which admit forbidden subgraph characterization. For example, line graphs, they admit a forbidden subgraph characterization, and there is a list of 9 graphs which is forbidden for the class of line graphs. And this is one type of characterization. So now we have a result A class of graphs admit forbidden subgraph characterization if and only if it has induced hereditary property. Now, what do you mean by induced hereditary property? This result was proved by Greenwell and et al. In 1973. And let us see what's the definition of induced hereditary property. A class C has induced hereditary property if G element of C implies that every induced subgraph of G also belongs to C. So a graph is said to have induced hereditary property. If G has that property, that means every induced subgraph also has that property. So is such a class is called is said to have induced hereditary property. Okay. Now we'll come to an example. You can see that this class. We'll go back to the slide. Okay, the class of graphs with gamma p g equal to gamma g does not admit forbidden subgraph characterization. So they proved this by showing that this class do not have induced hereditary property. So the example was like this. Okay, look at this example. You take C4 corona K2 complement. You can take, instead of C4, you can take CN. I'm taking just example, C4 corona K2 complement. You take, so this is C4 corona K2 complement. You have attached pendant vertices, okay, K2 complement. Now look, the power domination number of this graph is 4. You need these 4 vertices to power dominate it, and the domination number of this graph is also equal to 4. So this, for this graph and class of graphs like this, Cn corona Kn complement, you have gamma is equal to gamma p. Okay, the power domination number is equal to domination number, but you have a subgraph. This C4 is a subgraph of this, and for this subgraph you have gamma p equal to 1 and gamma of C4 is equal to 2. For this subgraph, gamma not equal to gamma p. So which means that this class, that is the class of graphs with gamma g equal to gamma pg, they do not have hereditary property. They do not have induced hereditary property. So it's not possible to characterize that class using any forbidden subgraph characterizations. Okay, so no, that type of characterization is not possible. You can try for some other type of characterizations. Then I'll try to give some of the results which we have in this area. In 2006, Henning and et al. Proved that gamma p of Pn box Pm, that is grid graphs, it is equal to ceiling of n plus 1 by 4 if n is congruent to 4 mod 8, and it is equal to ceiling of n by 4 otherwise. This was proved by Henning and et al. In 2006, and I'll show just figures for that. So this is P5 box P10. Okay, P5 box P10 Cartesian product. Okay, so you put PMUs at these 2 vertices. The first step, you will have the domination step, and then the propagation starts. So in the second step, you will have this much propagated. So this much vertices are monitored. It goes on propagation from here. Propagation goes like this. So the third step goes on like this, and you can see that with this, it is enough. These two vertices are enough to power dominate this grid graph. It is gamma p of P5 box P10 equal to 2. This is an example. Okay. Now coming back again, in 2011, myself and Daniela Ferraro and my guide, Professor Vijay Kumar, we have obtained a result that gamma p of HMN equal to ceiling of 2n by 3. And what do you mean by HMN? It is the honeycomb network. I'll show you the figure. So this is a honeycomb network, HM. This is actually HM3. Now, what do you mean by HM1? HM1 means just one single hexagon. It will form HM1. If you have one more layer of hexagon, it will form HM2. And if you here you have one more layer, so there are 3 layers here. So this is HM3. And we have proved that the value for this HM3, it is 2. So you put this PMUs here. This is one example of a power dominating set. And you cannot do it with one single vertex. You need at least 2. So this is a domination step. Then it goes on propagating like this. Goes on propagating, and you will get gamma P of HM3 equal to 2. This was the result we obtained. And we also obtained some results in grids, triangular grids. It's not rectangular grids. We have done it in triangular grids. Then some products we have done. We have fixing the graphs. Some of the products which we have obtained results. Then gamma P in some classes like cylinders, tori, generalized Peterson graph, triangular grids, product graphs are studied by various authors. Daniela Ferraro, she has done so many work in this power domination part. And I can show you references. My sister Seema Varghese has also done maybe some 4 or 5 papers in this. One of the papers is Paul Dorbeck, Seema Varghese, and Vijay Kumar, heredity for generalized power domination. She has done something on nodal graphs, then Hanoi graphs, all those things. That is also work in this direction. And these are the references. I think I would like to stop here. This first reference, it's a book, Fundamentals of Domination in Graph by Haynes, Sedentimi, and Slater. And this will give you all the papers and results which I have mentioned in the beginning, the first section of my talk about domination. And regarding power domination, this was the first paper that is Haynes, Sedentimi, Domination in Graphs Applied to Electric Networks in 2002. This was the first paper in graph theoretical terms. And there are many others. After this, many work is going on. And this paper, Henning, it was the note on power domination in grid graphs. It came in 2006, and this is our paper, Power Domination in Honeycomb Networks. It was in 2011, and this is my sister's paper. It is in 2016, and there are many more. Okay. So this is what I want to, and one more thing I would like to say is that there is another one direction in this direction of research in this area, that is studying polynomials with connected to this domination or power domination. See, there is a concept called chromatic polynomial. You may be familiar with that. Chromatic number means it is the number of ways of coloring a graph. So there is a chromatic polynomial, and looking at the chromatic polynomial, you can say about something about the chromatic number and so on. Likewise, there is a concept called a domination polynomial, and a lot of work is done over in that area also. And in power, there is a concept, it's already defined. Power domination polynomial is also defined, and some other work is going on in that area. And relating to power domination, one more thing I have to say is that power domination has a link to algebraic graph theory also. It's actually it is related to a concept called zero forcing number. It is related to the adjacency matrix of the. It's related to the rank and nullity of the adjacency matrix, all those things. Likewise, in that way, you can connect this power domination topic to algebraic graph theory also. That there are many works going on in this area. So it's a very dynamic area, domination and power domination and other types of dominations, Roman domination, secure domination, Italian domination is there. Recently I heard a definition like that. So there are many types of domination and very interesting topics. And the only thing is that we should, whenever you do a work, we should ensure that you have a sufficient justification for doing that. Merely changing the definition and introducing a new type of domination doesn't, it's not something of much value. But if you have some justification for changing the definition, then it's good, and that will be appreciable. Okay, I would like to stop here, and if you have any questions, you can ask. And I'll try to answer whatever I know. I'm not going to answer all the questions.
Now the presentation is over. It's time to clarify your doubts, and you can take some time to ask the questions. Otherwise, you can put your questions into the question box in your control panel. Ma'am, can you see the questions in Q&A, or I will?
Yeah, I can. The first question is, please give an example for D. I think, is it for dominating set? I have given an example. The second question, dominating sounds like counterpositive of cut set. How are they different? Cut set, it's something which disconnects the graph. There may be some relation, but not. I don't think so. It's that much related. Okay. Then, any research between vulnerability measures and domination numbers? Domination number, I think you are asking about the fault tolerance or something like that. Maybe there may be a lot of work is going on, and to be updated in every direction, it's not easy. But you can try. You can just look for it. Domination energy. Sorry to say, I haven't read anything on domination energy. Maybe if there is a talk like that. Someone has asked, could you please explain the power domination propagation rule once again? The propagation rule says that there are only two rules for power domination. First one is when you place a vertex, when you place a PMU at a vertex, that vertex and all its neighbors are dominated. And the second rule is if you have a power dominated vertex and whose all the neighbors except one is not power dominated, then you can dominate that also. That is the propagation rule. And is there any possible to use power domination in distance oriented graph? Yes, distance plays a very important role. Actually, there is a concept of time. How much time will you take? Say for a path, if you path power domination number equal to 1. So if you put a vertex at the first end, at the first end point, it will take much time to propagate till you reach the next end. Okay, so there is a propagation time or propagation step. Now, instead of putting it in the first vertex, in the end vertex, if you are putting it in the middle vertex, the propagation time will be less. So it is something related to distance, something related to time also. So there is some scope in doing that distance graphs. About lollipop, sorry, I don't know the definition of a lollipop. How can we take this domination concept in hypergraphs and semi-hypergraphs? Yes, something is done in hypergraphs also. Power domination and domination is done. Some results are there in hypergraphs, but I haven't gone through it. Can you suggest some topic on coloring of a graph? Actually, I haven't read much on coloring. But there is a different idea called zero forcing number. I told you it's directly related to this power domination number, but it's a type of coloring, but not the coloring which you refer to. Maybe there are so many areas in coloring you can refer. Okay, I haven't read much on coloring. Ma'am, do you know graph pebbling? Sorry, I don't know graph pebbling. And I hope all the questions are answered. Only 12 of them. I have answered all the questions. Anyone else?
No, ma'am. I think we have covered all our
Okay.
questions.
Okay.
Okay, thank you, ma'am.
So thank you for your patient listening, and all the best for your future work.
Thank you, ma'am. On behalf of Universal Engineering College, I would like to express our profound gratitude to the presenter of our last day FDP, Dr. Seema Varghese. Thank you very much for each and everyone for making our FDP a really successful one. We greatly appreciate the presentation you gave to us. It was nothing short of incredibly informative and interesting. Thank you, ma'am. Next, we have the validatory session. Before starting, I would like to inform you the followings. Please fill up the feedback forms and or attendance sheet which is available in the chat box. It will be available for 20 minutes only. It will be considered as your attendance sheet. Also, I would like to request you to post your feedbacks in the chat box. You can watch video lectures of our FDP again anytime from our college YouTube channel. We are glad to inform you that today we are presenting our resource person again to share their experiences with us. Now I invite Dhanya ma'am, the program coordinator, for welcoming all.
Good afternoon to all. I am Dhanya, one of the coordinator. Respected Vice Chairman P.K. Salim sir, Principal Dr. Jose K. Jacob, IQAC Director and HOD of ASH Department, Dr. K.K. Narayan sir, our resource persons, Sister Dr. K.A. Jermina, Dr. Lisa Matthew, Dr. Ramkumar P.B., Dr. Sudev Nadavat, Dr. Seema Varghese, all faculty of Universal Engineering College, and my dear participants. It's my pleasure to announce you that the 5-day faculty development program organized by Department of Applied Sciences and Humanities in association with IQAC comes to an end today. Only the validatory function remains. As a coordinator of this FTP, let me say a few words. Firstly, with immense respect, I welcome Salim sir, our chairman, Joe sir, our principal, Narayan sir, our HOD, to this validatory function. Also, I warmly welcome all of our resource persons, Sister Jana ma'am, Lisa ma'am, Ramkumar sir, Sudev sir, and Seema miss. It seems very happy to see all the resource persons on the same platform. But sister was not able to join due to some official matters. Sudev sir is also not able to join, I think, because of net issues. Hoping he will join soon. Finally, I welcome all the faculty of Universal Engineering College and all my dear participants present here for the FTP. In the inaugural session, I mentioned that we got the spark of this FTP accidentally. When we approached the resource persons, none of them denied us. Instead, they appreciated the task we are taking. In spite of the busy schedule, they all agreed to spare 2 hours for us. 2 hours for a live class, but we know they have to spend more than 1 day for the preparation of PPTs. Even though they were all ready to deliver lecture for us. Their willingness made this event a really remarkable one. As a result, we got 958 registrations within 3 days. Number of viewers through Zoom link was full every day. On an average, around 350 to 400 viewers each day through both Zoom and YouTube Live. Lecture videos in our college YouTube channel got a coverage of 1K, sometimes more than 1K viewers in the same day itself. Besides that, the feedbacks and comments of the participants through WhatsApp and emails. We never expected such a huge response. Those credits are all goes to our respected resource persons. We really appreciate the presentation you gave to us. And to my dear participants, thank you so much for your presence and responses on each day. I hope this FDP will fetch you into deeper understanding and friendship with one another. All of our resource persons are ready to share their PPTs with you. Also, they are ready to clarify your doubts through emails. Finally, to Salim sir and Joe sir, without your support, we will not have a platform like this. Your guidance and moral support always keep us positive and encouraging. And to Narayan sir, nothing to say, you are the backbone of this FDP. Once again, welcome you all to this valedictory function. Thank you.
Thank you, Dana ma'am. Next, I invite PK Salim sir, Vice Chairman of Universal Engineering College. Please, sir.
Thank you, Danya. Honorable Principal, Dr. Joske Jacob, HOD of the Applied Sciences and Humanities Department, Dr. K. Narayanan, beloved faculties, participants, and my dear friends, warm welcome to all. On behalf of the UAC management, I would like to express my sincere thanks to our Honorable Principal, HOD, and faculties of the Applied Sciences and Humanities Department, and all other technical and non-technical staff of UEC for hosting an extraordinary faculty development program. This program was watched by a huge number of participants from all over the globe. And I am very proud to say that the program was a huge success. All the sessions were informative, and the discussed areas are of great benefit to the participants, as the topics match with the academic curriculum. The program were successfully handled by well-experienced personalities of reputed institutions and universities. I would like to take this opportunity to express my gratitude and appreciation to the speakers of this FDP for their valuable contribution to make this program a huge success. Receiving an overwhelming response from participants, this 5-day FDP on discrete mathematics, graphic theory, and its applications, completing today after this session. With this, once again, I express my sincere thanks to all for making this program a very big success. Thank you. Thank you. Thank you.
Thank you, sir. Next, I invite Dr. Joske Jacob, our principal, Universal Engineering College. Please, sir.
Thank you, Adra. Respected Vice Chairman Salim sir, speakers, and my dear HOD, as well as the coordinators and my dear colleagues. So we have ended with we are ending the program, FDP program today, 5 days faculty development program. In my experience, this was a huge success, and all sessions were really informative. And I was already watching almost all sessions, and it was really good sessions. It was student-friendly session. It was really the question session was also really informative. And on behalf of Universal Engineering College, I express our sincere thanks to all speakers for your valuable time with us. And I take this opportunity to congratulate all faculty members and HOD of Applied Science and Humanities Department for arranging such a wonderful session. And thank you very much.
Thank you, sir. Next, I invite Dr. K. Narayan, sir, IQAC Director and Head of the Department, Applied Science and Humanities. Please, sir.
Thank you, Adira. Respected Vice Chairman, Mr. P.K. Salim, respected Principal, Dr. Joske Jacob, our distinguished resource persons, dear participants, and dear colleagues. Good afternoon to all of you. Today, we are at the fag end of our 5-day FDP on discrete mathematics, graph theory, and its applications. To our surprise, there was a huge response from all over the community or area, all over India. Even though we are blaming the COVID-19 pandemic, this is a positive aspect of that pandemic situation, I think. Otherwise, we could have accommodated participants only 30 to 40, like that. In every FPP program, we used to see like that. And moreover, when we are coming to the resource persons, we are very lucky in getting such resource persons. All the resource persons are veterans in their field, and moreover, they were equally competent. And definitely, the participants might have benefited. They are having a more benefit because of this FDP, I think. So thank you, all the resource persons and dear participants who are the part and pulse of this program. This FTP began with a spark in the minds of two assistant professors of my department, Kanya and Rahul Ravi. And it was a grand success, and I utilized this occasion to congratulate both of them. Moreover, there is a core committee behind the curtains. Without their work, this would not have been a success. A special congratulations to the entire core committee team. Every day, FDP starts with a nice introduction in a melodious voice by our gifted anchors, Suprabha and Adira. Both of you did it well, and utilize this occasion to congratulate both of you. And regarding the technical support by the college, whenever I say a technical session from the college, it's forgettable. Every time I see a man with a neckband around his neck, sitting in front of the system around the clock. None other than Mr. Shafi, a bouquet soaked in gratitude is presented to Shafi in this occasion. So once again, thank you all, and all the participants and our resource persons for making this venture a grand success. Thank you all.
Thank you, sir. Next, I invite our resource person to share their experiences. Dr. Lisa Matthew, Professor and Head of the Department of Mathematics, Amal Jyoti College of Engineering, Kanyirapalli. Please, ma'am.
Respected Vice Chairman, Mr. P.K. Salim, Principal, Dr. Joske Jacob, HOD of Applied Sciences and Humanities and IQAC Director, Dr. K.K. Narayan, my fellow resource persons, Sister Dr. Jamina, Dr. Ramkumar, Dr. Sudev, and Dr. Seema, coordinators of this program, Mr. Rahul and Ms. Danya. It gives me great pleasure to be among you once again at the close of the 5-day faculty development program on discrete mathematics and graph theory. Although I was not able to watch all the sessions live, I managed to watch them on YouTube every evening. As stated by Narayan sir, one positive fallout of the COVID-19 pandemic is that we are able to learn so much more from each other because of the number of webinars organized nowadays. But one feature which made this webinar notable was the meticulous planning, for which I heartily congratulate the organizers. I am sure that the participants, as well as all the other resource persons, will agree with me when I say that each of us has gained something during this program. The program will definitely benefit the young computer science and IT students of Kerala Technological University who start the new semester with a clear understanding of the close links between computer science and discrete mathematics, including graph theory. On the other hand, the research scholars have also benefited in that they have got a clearer idea of some of the important concepts in graph theory, such as labeling, domination, and graph algorithms. This program has also opened our eyes to the possibilities of research involving these areas. Probably one or more faculty development programs or conferences covering more advanced areas in these areas could be organized. Once more, I'd like to thank the organizers, Mr. Rahul and Ms. Danya, for inviting me as a resource person. I would also like to thank my colleague, Mr. Anish, who is the link between Mr. Rahul and me. He also was available with me for technical support during my session. I thank all the participants for their overwhelming response during my talk and also on YouTube later. Thank you all once again.
Thank you, ma'am. Dr. Ramkumar PB, Head of the Department of Mathematics, Rajagiri College of Engineering, Kakinad. Please, sir.
Okay. Good afternoon. I would like to congratulate management department for conducting this FDP, especially on this particular topic, discrete mathematics and graph theory and its application. So nowadays, discrete mathematics and graph theory plays an important role in application point of view. Because of the interdisciplinary nature, I think there are so many participated, so many students, research scholars and faculty members already participated in this particular FDP. So that shows the they are interested in doing research or to get more understanding about the application. I think nowadays these topics are very, very relevant. So we need to find out so many other areas of application of these particular topics, graph theory and discrete mathematics, especially lattice theory, partial ordering. And I would like to thank Rahul sir and Danya ma'am for inviting me to give this presentation. Okay, thank you all. Once again, I would like to congratulate the department to conduct this particular FTP. Okay, thank you.
Thank you, sir. Dr. Seema Varghese, Associate Professor, Department of Mathematics, Government Engineering College, Thrissur. Please, ma'am.
Okay. Respected dignitaries, it was very nice experience being with this webinar. Actually, it gave me an opportunity to brush up all my research work. I was going back to my research days. Recently, I'm sorry to say that I am not that updated, but this gave me an opportunity to do that. I have read all my research papers which I have done during those days, and also I was very happy to introduce the topics and the participants. I hope the participants have benefited with it. And I would like to appreciate the management and staff of Universal Engineering College for their tremendous effort to bringing together all these in one platform. All the research scholars, faculty members, students, and they were very eager to do this. And all the best to you for in your future ventures also. I would like to thank them for giving me an opportunity to be a speaker in this webinar. Especially I would like to thank Danya Miss and Rahul sir for this, for the technical support, everything. And in the beginning I had some problem, but it's okay, I managed to do it. And thank you all for this.
Thank you, ma'am. Finally, I invite one of the coordinator of our FDP, Mr. Rahul Ravi, Associate Professor, Universal Engineering College. Please, sir.
Good afternoon, all. I am Rahul Ravi, one of the coordinators of FDP. Our FDP, Discrete Mathematics and Graph Theory, and its application is a 5-day program organized by Department of Applied Sciences and Humanities in association with the IQAC. Discrete mathematics and graph theory are the main two branches of mathematics, which gives many opportunities in research area. This FTP will help the researchers and students in all engineering branches, especially from the computer science department. Discrete mathematics is the backbone of the computer science. Now, I would like to express my sincere thanks to the speakers and different days in FTP. Sister Dr. Jamina K. HOD, Associate Professor, Central University, Kasargod. She handles the first day sessions about labeling and its applications in graph theory. Thank you, ma'am, for your valuable knowledge. The second day was successfully handled by Dr. Lisa Matthew, HOD, Professor, Amalchodi College of Engineering, about the topic combinatories. Thank you, ma'am, for your presentation. Next, Dr. Ramkumar PV, HOD, Rajagiri College of Engineering, gave a detailed presentation about the partial ordering and lattices and its application on the third day. Thank you, sir, for your sharing knowledge. And the fourth day sessions wonderfully handled by Dr. Sudev Nadwath, Associate Professor, Christ University, Bangalore. Thank you, sir, for your valuable information. Today is the last sessions was handled by Dr. Seema Varghese, Associate Professor, Government Engineering College, Thrissur, about the topic Dominations and Variations in Graph. Thank you, ma'am, for your detailed session. Next, I would like to express the thanks to Mr. Salim PK, the Vice Chairman of Universal Engineering College, for giving all the support from the management side. Our principal, Dr. Jose K. Jacobs, sir, heartful thanks to you for your infinite support and valuable advice. Without you, this FDP will support, and without you, this FDP will not be a success. Next, the backbone of ASS department and IQAC, our HOD, Dr. KK Narayanan. Sir, your guidelines helped a lot in this program from beginning until now. Thank you so much, sir. Also, I would like to express the wholehearted thanks to Mr. Muhammad Shafi, the technical head of Universal Engineering College, for providing all the technical support for the FTP. Next, my sincere gratitude to Mr. Nigel C., Assistant Professor, Department of Civil Engineering, and John Abraham, Assistant Professor in Mechanical Department, for providing unconditional support and helping for the FTP. Catching the brochure and elegant certificates were designed by our student Anandu Murali from S5 Mechanical Department. Thank you, Anandu, for your beautiful design work. Next, the working hand behind this FDP program coordinator, Ms. Danya CG, Assistant Professor, AS&H, and all other faculties in Executive Committee. I express my sincere gratitude to all of you for your endless effort. Once again, I express the thanks to all of you. Thank you all.
Thank you, sir. Now we have feedback session from the participants. If any of our attendees want to share your experience about our FTP, you can raise your hand. Okay, we have Chandra Naik. Chandra Naik, please unmute and speak. Okay, we have Shubhi Saxena.
Yes, ma'am.
Yes, you can share your experience.
Okay, ma'am. Good afternoon, everyone. I'm Shubhi Saxena from UP, Kanpur. Actually, I have completed my master's in applied mathematics from CSGM University, Kanpur, and currently I am preparing for PhD. So this program is really helpful to me for understanding subject closely through such great professors who gave their wonderful talks. All lectures were knowledgeable and helpful, but I really like partially ordering lattices and its application by Professor Ramkumar PB, and also today's talk by Ma'am Seema Varghese. Ma'am, I'm able to know more about lasers and Hess diagram due to this lectures. I'm really thankful to all of you for providing me such a great opportunity to learning new things and helping me for understanding better mathematics. I'm really grateful to all of you. Thank you so much, ma'am. Thank you so much to all of you.
Thank you, Shubhi. Now we have Sri Devi.
Good morning, ma'am. Good morning, everybody. I first of all thank all the organizers for conducting such a beautiful workshop on discrete mathematics, especially graph theory. And I would thank all the speakers who have given a wonderful session. And I would request the organizers to conduct more workshops, more FTPs on graph theory and its application in various fields. Also, I would like to say that the sessions by every speakers was really helpful, and I will be able to watch it over and over again from your YouTube channel. That is the first plus point I have noted. Also, I thank all the organizers and also the Universal College for conducting and organizing such a beautiful work. Thank you so much.
Thank you, Sridevi. Now we have Gnanasekhar M.
Hello.
Yes, sir, you can share.
First of all, I would thank to the organizing committee and for conducting this wonderful session. So it's really very helpful for the young researchers. Yes, all the resource persons are really very expert in graph theory. Thank you for the organizing team, the resource person, and the technology. The technology is one of the most important role in the pandemic period. It was helpful to connect all the people. So thank you for again.
Thank you, sir. Now we will have a wind up. Once again, on behalf of Universal Engineering College, I express our sincere thanks to one and all. And I would like to thank all of us who were behind and in front of this program for these 5 days. Thank you. Stay safe, stay healthy.
Thank you. Thank you.